I welcome you to this third session of photochemistry. So, in this session, we'll discuss about photosensitization, photochemical equilibrium, examples, singlet and triplet states, photophysical processes like fluorescence, phosphorescence, chemiluminescence, sensors, etc. So, to recap or recollect the brief what we had discussed in the previous class. The previous class we discussed about quantum efficiency, examples of reactions having high quantum yield, and few examples for reactions having low quantum yield, and the reasons for high or low quantum yield. Photosensitized reactions. Many photochemical reactions, the reactant molecule does not absorb the radiation required for the reaction, and reaction does not occur. Certain compounds like mercury, if present, the mercury atom absorbs the incident radiation and subsequently transfer its energy to the reactant molecule, which is activated, causing the reaction to occur. A compound which can both absorb and transfer radiant energy for activation of the reactant molecule is called a photosensitizer. The reaction so caused is called a photosensitized reaction. So, in many photochemical reactions, what happens is the reactant molecule does not absorb the radiation to which it is exposed, and the reaction will not occur. If some foreign compounds such as mercury or cadmium, if they are present in the reaction mixture, these foreign substances they initiate the reaction. How do they initiate the reaction? They absorb the incident radiation and they transfer the energy to the reactant molecule, making the reactant molecule to react. So those substances which act as a carrier of energy, which activates the reactant molecule, are called photosensitizers. And the reaction so caused is called photosensitized reaction. And the process of initiating a reaction by the use of a substance capable of absorbing light and transferring the energy of the desired reactant is called photosensitization. And this process of initiating a reaction by use of photosensitizers is called photosensitization. So commonly used photosensitizers are mercury, cadmium, noble gases like xenon, zinc, benzophenone, and few organic dyes. So mercury atom absorbs the incident radiation and gets excited. The excited atom collides with the reactant molecule and transfers the excitation energy. This energy is enough to activate the molecule. The mercury atom returns to the original inactivated state. See here, mercury atom, which is a photosensitizer, it absorbs the energy and it gets activated. Now, this activated mercury atom it transfers the energy to the reactant molecule A. So once it transfers its energy, it returns back to its original inactivated state. So now the reactant molecule gets activated and the reaction will take place. Dissociation of hydrogen molecule in the presence of mercury vapors. So mercury acts as a photosensitizer here. So hydrogen molecule when exposed to light, it doesn't dissociate to hydrogen atoms. However, when this hydrogen molecule is exposed to light in the presence of photosensitizer such as mercury, the hydrogen molecule is dissociated to hydrogen atoms. So mercury on exposure to light get activated. The activated mercury atom transfers its energy to hydrogen molecule. Thus, hydrogen molecule gets dissociated to hydrogen atoms. So the dissociated hydrogen atom combines with CO to form HCO radical. HCO radical subsequently reacts with hydrogen molecule to form formaldehyde. The HCO radicals may combine to form formaldehyde or glycol. So these are the subsequent reactions of hydrogen atoms. So another example for photosensitizer is chlorophyll. Chlorophyll acts as a photosensitizer in photosynthesis. So we know that green plants prepare carbohydrates with the help of carbon dioxide and water and exposure to sunlight in the presence of chlorophyll. Here, the chlorophyll acts as a photosensitizer. Next is photostationary equilibrium. In a photochemical reaction, a state may reach when the rate of forward reaction may become equal to the rate of backward reaction. This stage is called photostationary equilibrium. In a photochemical reaction, at some stage, when the rate of forward reaction is equal to the rate of backward reaction, this stage is called photostationary equilibrium. So at this stage, absorbance of light produce no further chemical change. So example for a photostationary equilibrium, example of a reaction which shows photostationary equilibrium as decomposition of sulfur trioxide. So the forward reaction, that is the decomposition of sulfur trioxide to sulfur dioxide and oxygen, is a photochemical reaction, whereas the reverse reaction, that is the oxidation of sulfur dioxide to sulfur trioxide, is a dark reaction. At some stage, this forward reaction, the rate of forward reaction and the rate of backward reaction become equal. This stage is called photostationary equilibrium. So, few other examples of reactions which shows photostationary equilibrium is dimerization of anthracene, transformation of maleic acid to fumaric, singlet and triplet states. The electronic states of most organic molecules can be divided into singlet states and triplet states. Singlet state. A singlet state is a molecular electronic state such that all electron spins are paired. So we know that in organic molecules, all the electrons are paired in their ground state. So such a molecular electronic state where all the electron spins are paired, we call it a singlet. However, upon excitation of electrons, if the excited electron is no longer paired with the ground state electron, if they are parallel or they have the same spin, we call it as a triplet state. So you can see here, in this case, the excited electron, this is the ground state electron and this is the excited electron. If the excited electron have the same spin as that of the ground state electron, we call this as a triplet state. So this is the singlet state, excited singlet state. Here the excited electron has opposite spin than when compared to the ground state electron. So this is the excited singlet state and this is the excited triplet state. Next we will discuss about photophysical processes. Photophysical processes, fluorescence. Certain molecules or substances, when exposed to light radiation, they absorb energy and then immediately start re-emitting the energy. Such substances are called fluorescent substances. The phenomena is called fluorescence. So few substances or molecules, when exposed to light, they will absorb energy. They absorb energy and instantaneously they start re-emitting the energy. So those substances are called fluorescent substances and the phenomena is called fluorescence. And the absorption and re-emission of the light is not more than 10 to the power of minus 9 seconds. So this is the duration, 10 to the within 10 to the power of minus 9 seconds, the absorption and re-emission will take place. So the emission of light or fluorescence stops at once when the irradiating light is removed. So this fluorescence will stop when the irradiating light is removed. At once it will stop. So if you stop radiating the molecule, so it will stop re-emitting the light. So this emission of light will be stopped at once when you remove the irradiating light. The radiation emitted in fluorescence has lower frequency than the incident radiation. So the radiation emitted will be having will be of lower frequency or of higher wavelength than that of the incident radiation, this fluorescence. So mercury vapors, when exposed to radiations having wavelength of 253 nanometer, the frequency of emitted radiation is same as that of incident radiation. This phenomenon is known as resonance fluorescence. So mercury vapors show resonance fluorescence. So as I explained earlier, that in fluorescence there will be absorption of light by the molecule and there will be re-emission of light in the form of radiation. And during this re-emission, if the re-emitted radiation has the wavelength the same as that of the incident radiation, the phenomenon is called as resonance fluorescence. The mercury vapors exhibit resonance fluorescence. So examples of fluorescence. So organic dyes such as eosin and fluorescent, petroleum, chlorophyll, fluoride, that is calcium difluoride, uranyl sulfate, vapors of mercury are the few molecules which exhibit fluorescence. Next, phosphorescence. When a substance absorbs radiation of high frequency and emits light, even after the incident radiation is cut off, the process is called phosphorescence. The substance which shows phosphorescence is called phosphorescent substance. Emission of radiation takes place slowly, 10 to the power of minus 4 to 10 to the power of minus 1 second. So we saw earlier in case of fluorescence, the fluorescent material will absorb the light and instantaneously they re-emit the light. And this re-emission of light will be stopped at once when the source of radiation is removed. There are few materials such as phosphorescent materials called as phosphorescent materials. They will emit the light or they will glow even after the source of light is removed. Such substances are called phosphorescent substances, and the phenomena and the process is called phosphorescence. So here, in case of phosphorescence, it is a type of delayed fluorescence where the emission of radiation takes place slowly. Whereas in case of fluorescence, the emission of radiation was very rapid. So the molecules which exhibit phosphorescence are zinc sulfide, sulfates of calcium, barium, and strontium. So fluorescent and boric acid also will exhibit fluorescence. So chemiluminescence. Some chemical reactions are accompanied by the emission of physical light at ordinary temperature. The emission of light as a result of chemical action is called chemiluminescence. The reaction is referred to as chemiluminescent reactions. So we know that there are few chemical reactions which proceed by the emission of visible light. So those reactions which proceed by emission of visible light are called chemiluminescent reaction, and this process of emission of light as a result of chemical action is called chemiluminescence. So such a reaction is the reverse of photochemical reaction which proceeds by the absorption. So in chemiluminescence there will be emission of light as a result of chemical action, whereas in photochemical reaction there will be the absorption of light and the reaction will proceed. So the light emitted in a chemiluminescent reaction is also called cold light because it is produced at ordinary temperature. So the light emitted by glowworms, these are fireflies, you can see the fireflies. So here there will be oxidation of luciferin. Luciferin is a protein present in their body. So this luciferin, due to the aerial oxidation of luciferin by the enzyme luciferase, there will be emission of light. So this is chemiluminescence. So emission of visible light due to chemical reaction that occurs in the living organism is called bioluminescence. So bioluminescence is a type of chemiluminescence where it takes place in living organisms, where the phenomenon is seen in living organisms. Chemical sensors. Chemical sensors are measurement devices that convert a chemical or physical property of a specific analyte into a measurable signal whose magnitude is normally proportional to the concentration of the analyte. So, chemical sensors are nothing but the measurement devices which convert the chemical or physical properties of a specific analyte into a measurable signal. So, they have wide applications in different fields such as medicine, safety, environmental pollution, and many other fields. So, breath analyzer is a chemical sensor. So, this breath analyzer is used by traffic uh, policemen to check whether there is a consumption of alcohol. So when people consume alcohol, they exhale an amount of alcohol molecules directly proportional to the amount they drink. So breath analyzer is a chemical sensor, and other type of chemical sensors are electrochemical sensors. So this is the summary of this session. In this session, we discussed about photosensitization, photostationary equilibrium, singlet and triplet states, fluorescence, phosphorescence. Fluorescence and phosphorescence are photophysical processes, and we also saw chemiluminescence, bioluminescence, and chemical sensors. Thank you.